Alright, so time for part 2 for adiabatic quantum. So MVQC that we looked at previous hour, it was still fairly similar to circuit model. We just changed order of operations slightly. But adiabatic quantum computation is more different. So the idea is that you have some time-dependent Hamiltonian. And this Hamiltonian, it starts out being some Hamiltonian H0, and it ends up being some other Hamiltonian H1 as we increase time from 0 to tau, final time. So H0 is some EC Hamiltonian with a known ground state. So for this Hamiltonian we can prepare the system in its ground state. It's assumed to be simple. Then H1 is another Hamiltonian that's more complicated. It's so complicated that the ground state of this H1 encodes the solution to some optimization problem. Some problem. And now, since we can initialize the system in this known ground state, the idea is if we can let time evolve slowly enough, changing H0 into H1. If we do it slowly enough, we should have the system remaining in its ground state for the whole time. And after this time tau, we will then be, the system will be in this state that we then can measure to extract the solution to whatever problem we're trying to solve. So a slow enough change that the system remains in its ground state. We'll say ground state a lot, so let's call it GS. Okay, what does slow enough mean? This is another way to say adiabatic.
Can you express that as a sort of ratio of any?
Yes, we will. So far it's just words. We would like to put numbers, but hence the name adiabatic quantum computation.
A question.
Yes.
You said that it remains in its ground state, the ground state to H0 then?
No. So as when you are letting time evolve here, you see that the Hamiltonian system is changing from, at first it's only H0, at the end it's only H1, in between it's some mix of them.
Oh, okay, alright.
So you're slowly changing what the Hamiltonian is, you're slowly changing
What the ground
energy penalties in the system, or couplings in the system.
Right.
And so it's a new Hamiltonian every time step, it has a new ground state. But if you started in the ground state, and if the change is slow enough, then you will be in the ground state for that next Hamiltonian, so the next time step. And if you can do it all the way until you reach the final Hamiltonian, you will be in that ground state, which tells you the solution to the problem you wanted to solve. Okay, this is rather closely related to another method called quantum annealing. I won't say too much about that. Also in quantum annealing, the goal is to, at the end of your computation, you will reach the ground state of a system, and that system will be have some Hamiltonian, which means that the ground state encodes the solution to the problem. However, in quantum annealing, you don't need to start in the ground state of some other Hamiltonian. So quantum annealing doesn't necessarily start in the ground state. And doesn't need to be adiabatic. In quantum annealing, it's more like you can start in some excited state, and you have some thermal fluctuations, some quantum fluctuations, and then you anneal, so you gradually lower these fluctuations, and hopefully end up in the ground state at the end. Okay, so what is then the time scale for this evolution that we need to have in order for this to be slow enough? Well, the time evolution will be adiabatic if this time tau, the whole evolution, is much greater than Okay, so what does all this mean? Well, in the denominator here, these E0 and E1 are energies of the instantaneous ground state and first excited state. So basically we are looking here for the minimum energy gap between the ground state and the first excited state, somewhere during the evolution. The smaller that energy gap is at some point, the longer time you need to be adiabatic. And these psi 1 and psi 0 are the corresponding eigenstates.
Sorry, I have a question. If you don't know experimentally necessarily where your gap is going to be the smallest, right? So
Yes.
doesn't this make the assumption that you know how slow you need to move before you even begin the computation? Okay.
And actually, so this is sort of a problem here, that actually figure out what is that minimum energy gap
Is a hard
is a hard problem,
Yeah,
at least in many instances.
sure.
I guess also the solution to the problem is psi 0 at the 0 to 1, right?
That's right.
So if you knew that, you would
You're done.
Yeah. So bound is basically set by minimum energy gap. And yeah, this is hard to know what that is. Finding this gap is hard, or can be hard.
Does this assume that you're changing the Hamiltonian linearly?
Yeah, so, okay, that's sort of a simplified example. You can have other time dependent.
So is that taking into account in the time derivative there, or is that formula only valid for the linear case?
No, I think this is the general, correct me if I'm wrong, Pontus. I think this is
Yeah,
almost the thesis.
yes.
It's the maximum transition rate divided by the minimum energy. Yeah.
Yeah, that's what I.
Yeah, so that's a sort of a simplified example there for the Hamilton. But yeah, if there's any Hamilton with some time dependence, we start in one, you end up in another.
So I guess then that the denominator will not change dependent on the trajectory. Because S must go between 0 and 1, right? So you will explore
Yeah.
everything
Yes.
between there.
Yes.
Yeah.
That's right. So I guess setting this time dependence linear is sort of what minimizes this. Right? You want the numerator here to be as small as possible, and if the change there from H0 to H1 is not linear, then at some point it needs to be less, at some point it needs to be more, and it's this maximum that sets the limit. Okay, so this means it can be hard to know from any problems if adiabatic quantum computing works well or not. But there are problems where it's known that you can get a quantum speed up when doing adiabatic quantum computing. For example, there is a version of Grover's algorithm that you can do with adiabatic quantum computing.
Question?
Yes.
When you say quantum speed up, do you just mean like any kind of speed up a quantum computer could provide us, or?
And then I mean a speed up compared to a classical computer.
Right, right.
And
But it doesn't necessarily have to be.
It's not exponential necessarily. Grover is not an exponential.
Wasn't it proven that adiabatic quantum computing and gate-based quantum computing were polynomially equivalent?
Yes, I'm getting to it. I'm getting there. With some caveat.
Yeah.
Okay, let's erase the board first. Yes, as Chris was saying, and I was just going to say my next sentence basically. AQC is a universal model. Please get copy in the breaks. That's not exactly what Chris was saying. Chris was saying something more, something strong. But first of all, adiabatic quantum computing can be shown to be universal. You can do any quantum computation. If you can do with certain model, you could also do with an adiabatic quantum computing. AQC can be simulated efficiently again with polynomial overhead at least. By the circuit model. So that's maybe not too surprising. Circuit model we could do any quantum computation with. But so that was sort of proven first, and then a few years later it was proven the other way around. Meaning that if you can, with AQC, you can simulate the circuit model of quantum computation efficiently. So AQC is an efficient universal model for quantum computation. Now, in this discussion of whether you can simulate any quantum computation with AQC. It's often mentioned a certain term for describing what type the Hamiltonian is. And this term is stochasticity. So it's stochastic but spelled in a different way.
I thought it was stochastic.
Yeah, stochastic. I'm not sure how to pronounce it. Stochastic. Okay. Doesn't roll off the tongue exactly. So a Hamiltonian is called stochastic if the off-diagonal elements so x and y are eigenstates in some basis b, and x not equal y. So these are the off-diagonal elements of the Hamiltonian. If you can write the Hamiltonian in such a form, or find such a basis that the off-diagonal elements are
So they're all smaller than 1.
yeah, smaller than 0 or equal in some local basis. Then it's called stochastic and stochastic. And so the Hamiltonians that are stochastic seem to be somewhere, it's not clear, but somewhere around the border between classical and quantum. They are not extremely quantum.
And so the ones in the opposite regime, are they completely classical or completely quantum then?
No, so if it's non-stochastic, then it's more quantum. So, okay, non-stochastic.
And
Yes.
if it is 0, doesn't mean it's classical.
Unclear. Could be. I need to think about it. So it's not known if stochastic Hamiltonians can be simulated efficiently by a classical computer or not. It's possible, but yeah, no one knows. And it's also been shown that if you just have stochastic Hamiltonians, you cannot do universal quantum computation. Well, unless the polynomial hierarchy collapses, we discussed last time. But so it could be universal if the polynomial hierarchy collapses. No one thinks it will. So when they proved this thing that AQC can simulate the circuit model, it required that they really had non-stochastic Hamiltonian. So that's one condition on the Hamiltonians. Probably to do something really useful, you probably need some non-stochastic. But there are many Hamiltonians that are in use that are stochastic. It could be that stochastic Hamiltonians also can provide some of that. It's just unclear.
So the data elements can also be imaginary, right, or complex. So is it the magnitude that should be smaller than 0? Like sigma y, for example.
That's a good question. Let's. Well, you can have a magnitude that is smaller than 0, right?
That's true. Then,
So it can mean something else. Since it's formulated this way, I would guess that one limits these stochastic Hamiltonians to ones with real elements, because otherwise, yeah, as you say, it doesn't really make sense, the definition. I will check it. And
Yeah,
put
it
it in the
says
link.
it's,
Or maybe you found it already.
yeah, the stochastic Hamiltonian is one that has where the off-diagonal elements are real and non-positive.
Yeah.
Okay.
So,
So y is non-stochastic.
it's a real. Okay, so that was one good thing to know about the conditions on the Hamiltonian. The other thing is there's a condition on how the initial and the final Hamiltonian are allowed to be related. So requirement is that the initial and the final Hamiltonian should not commute. Yes.
I remember faintly that stochasticity was somehow linked to Monte Carlo simulations. What?
I don't know. It's the simple answer. I think maybe Laura or Julia knows more about these issues with stochastics. It's more their domain of expertise. Okay, so how can we understand this? Well, let's look at an example. This is from Pontus' master thesis. So we take just a single qubit. And that's our H naught, just sigma c. And then we take H1 to be -1 and -1/2 on the diagonal. Okay, so this will probably not do any useful computation, adiabatic evolution between these, but it's actually not even possible to do adiabatic evolution between these. So why is that? Well, the ground state, so let's label the states here as 0, as usual is 1, 0, 1 is 0, 1, So the ground state of H0 is state 1, because that has the lower energy. The ground state of H1 is 0, because that has the lower energy. H1. So, at some point, as we time evolve from H0 to H1, we must, the ground state must change from 1 to 0. And we can see if we do the time evolution, like before the linear time evolution, there will be a point where you have a degenerate ground state. 0 and 1 have the same energy. So at one point in the time evolution, so I mean these are both diagonal in the set basis, so you have two eigenstates and they will always be in that. So the gap will close. And we saw before this condition for the adiabatic evolution was that well, it was given by this energy gap in the denominator. So if that goes to 0, well, time for adiabatic evolution would go to infinity. Chris?
Could you maybe play tricks here where, okay, maybe the ground state becomes degenerate. You could possibly kick yourself into a higher state where you are no longer degenerate and then travel back down after the gap?
Well, that you can probably do, it's just not adiabatic evolution.
Sure. I guess, would you still have a speed up in like a diabatic?
It's also a very interesting question. So, the adiabatic algorithm sort of guarantees that you will end up in that ground state that you want to end up in.
Sure.
Now, there might, of course, be other time evolutions that are not adiabatic that could also take you there. But to give general recipes for that is probably difficult. And this gap closing here is basically, it's related here to the fact that these Hamiltonian is example commutes. So if the gap closes to the denominator in the adiabatic condition close to 0. So tau would go to infinity. Would you like to add something to this?
Well, I'm just thinking another way to think about is because both Hamiltonians here
Yeah.
are diagonal in the computational basis. So if both Hamiltonians commute here and we prepare the ground state of H0, then I believe maybe there's some just easy transformation to H1, and then if we could prepare H0 easily, then we could also prepare H1 easily.
Probably. This example is not chosen to show like, what a useful adiabatic quantum computation could be.
Yeah.
It's just to show how AQC could fail, or how it could fail.
Question on it?
Yes.
But it would fail for other, because you said that this is maybe a not so useful example then, because you could maybe do this efficiently anyway. Is it only in these types of cases where it fails, or is there other cases where it fails where we would like to do this? Because here this, because while it's great what you said now, that we could probably get H1 here easily anyway.
Yeah, I mean, if they commute, I believe there's some easy transformation from H0 to H1.
So then will this only fail in cases where it's easy to get H1 anyway? Because then it works when it should work. It fails when it's...
Well, as we said before at the beginning, determining what the minimum gap is a hard problem in many cases. So I'm very hesitant to make statements about that you somehow could do adiabatic computation easily in the cases that are easy, or sort of like the adiabatic computation only fails in cases that are easy anyway.
Because that's not the case. That's my question. Is that the case?
I don't think so.
Oh.
Okay, more questions?
Is it always easy to calculate this, if they commute or not? If they can always be done efficiently?
To take the commutator to Hamiltonians should
Yes, in principle, it's matrix multiplication.
Yeah.
should be.
I mean, I guess there could be that, you know, okay, you have a problem, so that will fix your H1. Because then you need to find a suitable H0 which does not commute.
Yeah, but yes, exactly. So your H0 it should not commute, and it should also be some simple Hamiltonian where you can,
Yeah.
you can prepare the ground state, and you should have a setup where you can theoretically change from H0 to H1.
Because H1 is usually fixed by the problem you want to solve, right?
Yes.
Yes. Okay, so next week on Tuesday there will be the first tutorial session. So Julia will demonstrate some exercises based on lectures from this week. So among other things, the C0 gate for measurement-based computation I mentioned today. I will see you in week 4 again, I believe, the lectures. Okay, that's all for today.